Let's briefly review wave behaviors. I've covered three major types of wave behaviors. First of all, interactions between waves and boundaries. Secondly, interactions between waves and obstacles. And finally, interactions between waves and other waves of the same type. First, let's consider the interactions between waves and boundaries. By boundaries, I mean the points at which the medium of propagation changes. For instance, you can have a light wave traveling through air that enters a lake. The point at which the water meets the air is the boundary. This is the point at which the medium of propagation changes. When a wave hits such a boundary, there are two primary options. Firstly, reflection, in which case the wave completely changes its direction. By the law of reflection, the angle of incidence is equal to the angle of reflection. So the light hitting a mirror, if it enters at 30 degrees, it also bounces off the mirror at 30 degrees. Secondly, there is refraction. This is a behavior that occurs when the wave is transmitted through another medium. For example, light hitting a water, some of the light will be reflected, but most of the light will be refracted. That is, it will travel through the water, but at a different angle than the angle of incidence. The angle of refraction is dependent on the difference in refractive index between the two media. The behavior of a wave after it interacts with an obstacle is governed by this idea of diffraction. Diffraction occurs when a wave encounters some sort of impermeable boundary. If this boundary has a slit, for instance, diffraction occurs on the other side of the slit, like so. This behavior very clearly distinguishes waves from particles. And finally, waves also interact with other waves. It's important to remember that waves interact with waves of the same type. Sound waves interact with sound waves, light waves interact with light waves, and so forth. This is important to remember because the idea of superposition doesn't make sense if you have light waves, for example, interacting with sound waves, because the type of amplitude is very different. In a light wave, the amplitude is measured in electric or magnetic field strength, whereas for a sound wave, the amplitude is measured in terms of pressure. You can't add magnetic field strength to pressure. It doesn't make sense. The units are too different. Let's consider a simple diffraction pattern. Let's say we have light that's passed through some sort of slit here and a second slit that's lower. We will observe a diffraction pattern like this. Can you identify the points at which you would have constructive interference and completely destructive interference? Let's take a look. Here you have two crests represented by the lines interfering. So you would see the greatest amplitude here because the two amplitudes have added at points where the center line, the imaginary center line that is, of one wave is interacting with the crest of another wave. You will see completely destructive interference if the amplitude of the two waves is the same. In this case, the amplitude is the same because it's the same wave. We had only one wave passing through the slits. You can have other cases, however, where two different waves from different sources are interacting, and you could see partial destructive interference at points such as this. That'll be all for our unit on wave behaviors.